Hello, this is Jack Jackson. In this video, I'm going to be showing you a GeoGebra activity that I put together to help explore hypergeometric binomial and normal distributions and how they compare to each other. So let me start by deselecting a few of these things here. And let's start with just a hypergeometric distribution. So if you check this box here, the hypergeometric will appear. And a hypergeometric distribution, what happens is you have some fixed population size. Right now it's set at 50. I can adjust that with the slider here or by just typing in a number. Let's go back to 50, let's say. And then you can have the number of successes in the population. Let's say for now that is 20. So there are 50 things out there. We're going to select from them a certain number of them. Right now it's set at 14. Let's make that 12. So we're going to select 12 things from this group of 50, and 20 of them are considered successes. The rest are considered failures. There are many, many real-world applications where this could be appropriate. And X, our random variable, is going to represent the number of successes in that sample. There are M successes, 20, in the population, and an unknown value of X in the sample. Now that random variable, in this case, could start at 0, could be 1, 2, 3, all the way up to and including the sample size of 12, but it has to be a whole number. All right, so we can see that here. Earlier videos talk about this in more detail in my playlist. Now, this one here, I could do various kinds of probabilities. So right now it's set on left tail probability, which I can adjust by this slider or by typing in a number here, and it shades those bars that are less than or equal to L. In this case, less than or equal to 3. So the probability is just adding up the heights of those shaded bars, and you can see that just displayed there. We can also do a right-tailed probability instead. That's controlled by this U, this upper one here. Let's see. There it is. Right-tailed. It's controlled by the upper. So this is, say, the probability that x is greater than or equal to 6. Now notice there are bars that go all the way out here to 12. They're so short it's a little hard to see on this particular scale. We could also do a middle probability, and that will be between L and U inclusive. So right now we're going from 3 up to 6, including the 3 and the 6. So we're adding the heights of these bars. That's also the same as adding the area of these bars because the widths are all 1. Okay, so then we could do a two-tail, which goes from forever left, which is really 0, up to the lower of 3, and from the upper up as far as it'll go to the right from 6 up to, well, the sample size, which is 12 in this case. And we can see how this will be adjusted if we slide these parameters that defined it and so forth. Now, if we click on this parameters thing, it will tell us some things about this hypergeometric. P is the proportion of successes in the population. That's big M over capital N. That's 20 over 50 or 0.4. Q is the probability, is the proportion of failures in the population. It's 1 minus P, or about 0.6, or exactly 0.6 in this case. P is also the probability of success, the first one we select. Q is the probability of failure, the first one we select. But as we select ones after this, the probability of success each time depends on what came earlier. So it will not it won't stay the same as P. The mean of this distribution is N times P, which is 4.48. And here's the formula for the standard deviation, which is about 1.49. Now, we can also compare and contrast this to a binomial approximation. So here's a binomial approximation with this setup. So basically we can think of a binomial distribution as the same setup as the hypergeometric. We have a population of size 50 and there are 20 successes, and we're going to choose 12. And we're counting the number of successes. So far hypergeometric and binomial are exactly the same. But in hypergeometric, the selection is done without replacing them. So we do not put the value back in, the item that we select the first time, we do not put it back in with the next selection. So the first selection will be out of 50, the second selection will be out of 49. The binomial, however, is the same thing as hypergeometric, except that we put it back in each time. So the selection is done with replacement. So that probability of success every time is P of 0.4. Mean is still n times P. The standard deviation is n times P times Q, which you notice is a little bit bigger than the standard deviation on the hypergeometric. And if you look, these bars are similar to that one. Here's just the binomial. Here is just the hypergeometric. Here's just the binomial. Or here's just the binomial. And then here they are together. And you can see that some of the bars in the middle here are a little shorter. The bars on the ends are a little bit bigger on the binomial than they are on the hypergeometric. Now, there's some difference here. So if you think of the hypergeometric as the actual situation, which is typically the case, in most cases when you go out and you do like say you do a survey or you're sampling of any kind, typically you do not allow the same item to be selected twice or more than once in the same sample. So typically it's very realistic for something to be hypergeometric. However, it turns out to do the probabilities here that we need to know the population size in order to figure out the probabilities for the hypergeometric. Whereas in the binomial approximation, it really doesn't matter what the population size is. All that really matters is this proportion of successes or the probability of a success each time, P. It's the same every time. Okay, so for that, we can sometimes use a binomial to approximate a hypergeometric. Now you notice here it's not a particularly good approximation. For example, if we want to do the probability that x is less than or equal to 3, the actual is the hypergeometric of 0.191085745, whatever, accurate to that many decimal places. The binomial approximation is here for a difference of 0.034 or something. So it's about 300ths bigger on the binomial than it is on the hypergeometric. And that could very well be an important difference there. So maybe not such a good approximation. But if we let the let's take this to 500 and 200, it's still the same on the binomial approximation now, but the hypergeometric is a different situation. So now think about it a minute. On the hypergeometric, the probability of success the first time is 0.4, same way on the binomial. On a binomial, the next time, the probability is still 0.4 because you're putting it back. Well, if you don't put it back, let's say you got a success the first time. The probability of success the second time is 199 over 499. That's very close to 200 over 500. Whereas when we were back at a size of, say, 50 and, say, 20 here, where we started, or especially if we were at a size of, say, 5, just say 5 here and 2 here, you can't even select 12, so that's kind of a wacky thing there. But let's go back to 50 and 20. Then what's going to happen here is that, 19 over 49, which will be a probability of success the second time if you got a success the first time, is somewhat significantly different than 20 over 50. But when we went up much bigger to, say, 500 and 200, that difference is much smaller. And so what it ends up doing is when you end up finding the probability here of these bars, if you look, it's really hard to tell. See, there's the binomial, there's the hypergeometric, there's both. There's some difference in the bars here, but there's very little difference. So that this error here it's not 0, but it's pretty small, 0.003. So if you don't need an answer to more than, say, 2 decimal places, then the binomial is just as good as a hypergeometric for that approximation. Well, this one will round off to 0.22. This one rounds off to 0.23. But the actual error is only about 0.003. So it can be a pretty good approximation when? Well, when the population size is pretty big. Okay, and then again, you can look at this again with a right-tailed, a two-tailed, or a middle probability for both of them. And again, we can hide or show the parameters there. Now, sometimes we also let's just go back to a left-tailed, let's say, and let's go back to the original of 50 and say 20. We can also sometimes use a normal approximation to both the binomial and the hypergeometric. So that's what we're going to get here. Now, if we use the standard deviation from the binomial, and notice that the mean is the same from the hypergeometric or binomial. So if we use that mean and standard deviation, which is what we have here, then we get this normal here. And you see it's not that bad an approximation of the binomial, maybe a little worse approximation from the, well, if it's an approximation of the binomial or the normal or the geometric. And if we said the probability that x is less than or equal to 3 here, we get this shaded area. And that's about 0.144. Well, that's actually under the hypergeometric by almost 5 hundredths, under by about 0.04666. So we see that the normal approximation is probably not that particularly good approximation there. It's off by quite a bit. Unfortunately, this is what is used a lot of the times when people are dealing with a situation that is truly hypergeometric, perhaps could be approximated by a binomial, but then a normal approximation is really not that particularly good. And part of the problem is the sample size is pretty small. The population size is pretty small. If I go up to 10 times as big here, now the binomial and the hypergeometric are pretty close, but look, the normal is still off by a considerable amount. So there's sort of two things that we can do that at least ought to help a little bit. One is we can adjust the standard deviation to be the standard deviation from the hypergeometric situation. Of course, you can do this if you know the population size. Well, let's see, how did that compare? It actually made the error a little bit worse in this case. Okay, and you can see a slight change there. Another thing that we can do is use what's called a discrete correction. A discrete correction is this. The discrete case, like the hypergeometric and the binomial, the x values are only, in this case, whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. That's it. That's only possibilities. So in this case, we're picking up whole bars at 0, 1, 2, and 3. There's really nothing between 3 and 4 to consider. When we did the normal approximation up to 3, we're just going up to here. But we might also consider including things that round off to 3. So that would take us all the way up to 3.5. And so this is what a discrete correction will do, will allow us to do that. Well, if you look, that actually helped quite a bit. That helped get the normal quite a bit better, whether we're using, in fact, the binomial standard deviation and the discrete correction is actually quite good in this particular case. Okay, but we could also look at, say, a middle value here. In this case, the hypergeometric standard deviation was a little better than the binomial. The discrete was way better. If you look without the discrete correction, this is off by a bunch. Okay, they're both under by over about negative. It's negative 0.14 something, negative 0.14, negative 0.15 in that vicinity. They're off by quite a bit. Okay, But if we include the discrete correction, it actually takes this lower one down to include things that round off to 3 and the upper one up to things that round off to 6. So we're actually going from 2.5 to 6.5 on the normal approximation. You can see that shaded here. If you just do the normal by itself, there it is. If you want to see it with, say, with the binomial there or with the hypergeometric. These errors are considering the hypergeometric as the actual one, figuring those out compared to them. And so we can see, even in this case, notice that NP and NQ are both 300, and yet without the discrete correction and using the binomial distribution standard deviation, it's off, the error is off by a lot here. Or if we do a two-tailed approximation, you know, it's off by that amount, which is a whole bunch. And oftentimes, I think that some textbooks have not a good condition, because I've seen conditions as low as NP and NQ both being as low as 15 in some books, as low as 20 in other books, or maybe 30 in other books. Well, here we have it at 200 and 300, and we see that that error is off by a lot. And if you're using this for inferential statistics, such as like a hypothesis test, that much of an error is going to give you a completely, might give you a completely different kind of conclusion than you would get otherwise. So I think that you know, this normal approximation is a good thing. It works. But I think it's also maybe a little overused, because in reality, nowadays, with programs like what you see right here, or even standard graphing calculators like a TI-84, for example, or other programs that you can look at online, or the standard probability calculator in GeoGebra, they will allow you to compute hypergeometric binomial as well as normal probability calculations very easily. And so you're really better off using the actual thing. So the actual thing most likely is actually hypergeometric, right? Hypergeometric is sampling without replacement. You can use a binomial to approximate that if the population size is big but unknown. If the population size is known, you might as well use the hypergeometric. But we can use binomial to approximate the hypergeometric if the population size is big, and there's really probably no need to go to the normal approximation. So anyway, you can experiment with this app in GeoGebra and experiment with different possibilities of seeing what's happening as you play around with these sliders and boxes and check boxes, and experiment with some different options there. So once again, hypergeometric is the most realistic situation. Oftentimes, however, we don't know the population size, so we use a binomial to approximate it. That's usually pretty good if the population size is big. And you can kind of see, well, how big? You can kind of play around with it here and see. We can use a normal to approximate the binomial. By the way, if you just want to compare a binomial and a normal, this error is for the related hypergeometric. But you could actually, if you're not given a population size, convert the probability of success, P, the parameter, to a fraction, put the numerator as M and the denominator as N, and then you can get this to work out. For this to make sense, it's probably better if N and M are both bigger than the sample size, so you could let this be what might be a good way to do it, would convert to a fraction and let the top take N times the top for M and N times the bottom for N, for big N, and N times the denominator for that, and that would give you a reasonable binomial, and then you could compare it to the normal there. Okay? Enjoy this. Bye-bye.